Today, after almost 3 months of experiments, I'm going to be getting the final results of my algae bloom project. Let's go. Hey, I'm Olion, and I'm once again experimenting with microalgae. This one's going to be a long one. Today, we're going to get through the results I've gotten from the past month of experimenting, including the results from my clay concrete composite and the modified clay flocculation. Essentially, all the results that I'm going to be presenting at my local science fair in just over a week. Let's talk about the modified clay flocculation first. Remember, the first goal of this experiment was to test how modified clay, essentially a powdery algae magnet, can flocculate and remove algae blooms out of water, and with what effectiveness they do that, and ultimately, what concentration of chitosan hydrochloride, a substance which makes clay positively charged, is best for removing algae from water. Now, the way I tested this, I explained last week, was by adding 1 milliliter of modified clay suspension to 10 milliliters of algae, and putting all of that in the bioreactor, a machine that measures the optical density of the solution, essentially how much light it absorbs. And by doing that, I got curves that look like this. Now, I pulled the raw data from all those curves, put them all in one big spreadsheet, and replicated those curves in Google Sheets here. And you can see there's 4 curves on this spreadsheet. There's the curve for 1 milliliter of chitosan for every 100 milliliters of clay, 2 milliliters, 5 milliliters, and 10 milliliters. If you need a deeper explanation of how exactly I made all the chitosan and set up the clay, you can check out one of my other videos in the top corner. Now, those scatter plots are honestly a little bit messy. It's hard to tell exactly what's going on, so I simplified them down to these curves over here. These are just the regression curves of an exponential regression, essentially, of the actual dots that you were seeing on the previous scatter plot. Now, it's pretty clear from these curves that there's a significant decrease over time in the optical density of the modified clay algae solution. One that reaches all the way super low to an optical density of 0.01. That's the optical density of water. Essentially, if you remove all the algae out of water using the modified clay, you're just left with clear water, which is indicated by that optical density of 0.01. So when I reached that point, I stopped the experiment and I considered everything completely flocculated. Now, the key data point that I really wanted to measure, in addition to these curves, is how much time it takes to get there for each amount of chitosan hydrochloride. And that's what I got in this graph over here. This graph shows, and plots, data points of how long it took to reach that value of 0.01 the first time for each amount of chitosan hydrochloride in solution. 1 milliliter, 2 milliliters, 5 milliliters, and 10 milliliters. And the data is actually kind of all over the place, which isn't entirely unexpected, to be honest. What we're seeing is that the lowest time to flocculate fully was with 2 milliliters of chitosan hydrochloride, and the highest was with 5 milliliters. You'd probably expect a downward trend, as in when you have 1 milliliter, it takes the longest, and when you have 10 milliliters, it takes the shortest. But that's not what's happening here. So clearly there's more complex things happening. To be honest, I'm not entirely sure what's going on quite yet. But I would understand that the modified clay, if you think about clay particles, might have a limit on how much chitosan they can absorb. So having higher concentrations of chitosan may not actually be that good, and might actually be interfering with the ability of the modified clay to absorb algae. So it's not entirely surprising that it works best at 2 milliliters. What's confusing me a little bit, though, is that the time taken to flocculate is actually lower at 10 milliliters than it is at 5 milliliters. And that's throwing me off a little bit. So I'm going to do a little bit more research and see if I can figure out why exactly that is. So that basically covers the modified clay flocculating the algae piece of this experiment. But there's another part, the clay concrete composite. Over this time, in addition to trying to flocculate algae with modified clay, I've also been trying to figure out a way to reuse that modified clay and make it into something useful. And that something useful is concrete. Specifically, mixing the clay into concrete to form a composite that is potentially stronger than the concrete that we're using in our buildings right now. Now, the way I tested this, which I explained in a number of my other videos, was to essentially make a bunch of little concrete discs, which I then destroyed with a clamp to see how much force it took to destroy them. But it turned out that that clamping process was actually a lot more complicated than I expected. Initially, and as I explained in one of my previous videos, I was going to be treating the clamp like a spring, but that ultimately way overvalued the strength of the concrete. So I did some further tests literally like 3 hours ago, where I took a clamp, the same clamp, and wound it onto a scale. Now, quick aside, the way a scale works is essentially it measures how much force whatever is on top of the scale is compressing down and applies a normal force back up. Now, the amount that it has to apply back up, once you divide by the acceleration due to gravity, gives you the mass of the thing on top. But you can also kind of trick the scale into thinking there's something stepping on it when it's not, essentially by putting a clamp on it. And that clamp, it essentially tells you a weight, even though there's no weight on the scale, it tells you the weight, which is directly correlated by the acceleration due to gravity to the force that the clamp is applying. It gets a little bit complicated, but essentially, I was able to figure out a relationship between the number of turns on the clamp, number of turns of the screw, to the amount of force that was being applied. And you can see that on screen right now. From there, I was able to take the number of turns that it took to break each of my concrete discs and plot them onto that line to figure out how much force was applied in order to break them. Now, in this process, I was testing concrete clay composites with 0, 2.5, 5, and 10% modified clay mixed into the concrete. And the results I got can be seen right here. This graph shows the concrete strength, essentially the pressure that it resists, which is about force over area, given the modified clay concentration that it had. Now, there are two interesting pieces of this graph. The first one is that it seems to obey some kind of normal distribution-esque shape, which is plotted on the screen along with it. Now, the reason why the normal distribution kind of bell curve-ish shape fits here is because there has to be a horizontal asymptote at 0. The reason for this is that the compressive strength of the concrete, no matter how much clay you put in there, cannot reach below 0. You can't have negative pressure. So there must be an asymptote at the horizontal at 0. Now, there's also some kind of maximum value. It kind of curves up like this. You can see it on the graph. So I chose the normal distribution as a possible curve to fit to this. That may not be the only curve, and I'm going to explore this over the next couple days. But right now what it's predicting is that there's a maximum value at around 2% concrete. 2% clay concrete, rather. In other words, when you add 2% clay and 98% concrete, you get a mixture that's actually stronger than the regular concrete that's in our buildings. That, to me, is super, super, super cool. That we can actually, using modified clay, make a concrete that would be viable in our world right now. Now, I will note right off the bat that the values I'm getting here are significantly lower than the values you'd expect for normal concrete in terms of compressive strength. Normal concrete has a compressive strength of several megapascals, millions of pascals, where I'm getting stuff in the range of 700,000 pascals, roughly. Now, that's not super far off, but it is far off enough to raise some alarm bells. Now, part of the reason why this might be happening is that my concrete circles were really, really thin. They're about 0.5 centimeters, or about 5 millimeters. And that means that they don't necessarily accumulate all the same compressive strength that you might get from an actual slab of concrete that's several inches thick. And I think that's a contributing factor to why they cracked so easily and why they don't resist as much force. But I'm going to look into that a little bit further as well. So there we go. That was a quick summary of all the results I've gotten over the last almost a month of experimenting, really. And I explained that in a pretty quick way, I think. But believe me, there have been quite a lot of ups and downs, repeating trials, trying to wrap my head around all the science that I'm doing here, but it's definitely been a ton of fun. Now, like I mentioned, I'm going to be presenting these results at the Ottawa Regional Science Fair in, like I said, just over a week. So if you're going to be there, I'd love to say hi. Let me know in the comments below or somewhere on LinkedIn. Just send me a message. I'd love to meet you. And I'll have more videos out, of course, of the science fair and of this project going forward in the future. So if you want to see more content like this, make sure to subscribe on YouTube, follow on LinkedIn, and as always, I'll see you in the next one.